Okay, so we've spent a lot of time recapping linear regression and getting that happy. But what we're going to start doing now is we're going to break it and then fix it. And the idea being that now we have this solid foundation of linear models, we can start adapting it for more and more situations. So the first thing we're going to look at is GLS, which is generalized least squares. So let's set up our model. So we've got a model y equals x beta plus epsilon, and epsilon's a random variable. And we're going to assume that the expected value with this is 0 and the variance is sigma squared I. So basically you have no covariance between the residuals and all the variance is on the diagonal and it's all the same variance. And what we're going to do is we're going to change that. We're going to start by saying, well, what happens if the variance of our epsilon is some sigma squared v? So instead of I, so instead of it just being ones along the diagonals, which get multiplied by the sigma squared, now we have some other structure. Now, we're going to have to be careful and just make sure we know that variances should be greater than or equal to 0. So we need to have some constraints on the v to make sure we're not going to mess up. So our v is going to be, it's going to be an n by n, a positive definite symmetric matrix. Okay. Well, what do we mean by symmetry? Well, what we mean is that if I take sigma squared Vij, so I go to my matrix V and I go to the ith row in the j column and I get that entry and I multiply that by sigma squared, that's going to be the covariance of epsilon I and epsilon j. We know because of the symmetry of covariance that has to be equal to the covariance of epsilon j, epsilon I. So that means that that entry in there, which is going to be the Vji entry times sigma squared, must be the same. So we have to have it symmetric. We can't somehow have suddenly the covariance change because covariance is a symmetric operator. Positive definite. Well, if I've got an n times n matrix, such that I take any old vector, as long as it's not the zero vector, so any vector at all, and I go, that vector A, transpose VA, that answer will be greater than 0. That means positive definite. Any A you want, as long as A is not equal to 0. If I take any A, and I now do the calculation A transpose VA, and that's greater than or equal to 0 for all A, we call that non-negative definite. Okay? So if it's always greater than 0, it's positive definite. If it's greater than or equal to 0, we call that non-negative definite. And we want this because if you think about it, I shouldn't be able to take some A transpose times my epsilons, take the variance of that, and get something that's not greater than or equal to 0. So if you think about it, if I take my A transpose epsilon and I calculate the variance, we've seen before that's going to be A transpose VA sigma squared at the front. So I need that to be greater than or equal to 0. Sigma squared is greater than or equal to 0, so I need A transpose VA to be greater than or equal to 0. Hence, I need V, for it to be okay, to be non-negative definite. In fact, we really don't want it, the variance of A transpose Y could equal 0. And because of that, if we did have that, it would mean that one of the observations is a linear function. The others would really want to eliminate any redundancy like that. So we're going to assume that V is positive definite. So we're just going to have that extra constraint. Okay. Well, we've got this model. You know, it's the same model before. We've got this y equals x beta plus some epsilon. The epsilon now has a strange variance, but we could just use our ordinary least squares. Our beta hat, which you know is x transpose x to the minus 1 x transpose y. That's fine. And you can check that the expected value of my beta hat ordinary squares is beta, so it's unbiased. But my variance now, we don't have that nice properties. You know, before the variance of your least squares in the standard model was just sigma squared x transpose x to minus 1. So it's just this first bit here. But now because we've got this more complicated variance structure, it becomes nasty. And in fact, so we could do this, but it's not optimal. Why is it optimal? Well, it's unbiased, so that's good. But the assumptions of the Gauss-Markov theorem do not hold. And because of that, it's not the best linear unbiased estimator. So we've got an unbiased linear estimator. It's good, but it's not as good as we can do. Can we improve it? Well, Gauss-Markov says we can, but how are we going to do that? Before that, we're going to talk about square root matrices. So first of all, let's take my V, which is, and in this case, it's any square symmetric matrix. It doesn't have to have all this positive, but let's take any symmetric. I can rewrite it. I can write it as the product of 3 matrices. Well, actually 2. An E, a lambda, and an E transpose. And the lambda is going to be interesting. Lambda is going to be basically a big matrix with zeros everywhere, but along the diagonal, it's going to have some numbers, and we'll call that the first number lambda 1, lambda 2, all the way up to lambda n. I'm also going to make it that basically the E is nice. That if I take, basically it's orthonormal. If I take any two columns and multiply them, they're at right angles to one another, so the dot product is 0. If I take any of the elements of the columns and I multiply it by itself, I get 1. So the whole idea is, what that means is that E transpose E equals E transpose, which equals I. So it's what we call orthonormal. So I've got this special setup. And the nice thing is first of all, if V is non-negative definite, then that will mean that all the lambda i's are greater than or equal to 0. And it will be positive definite if all of them are greater than 0. So remember, the lambdas are the numbers along this diagonal matrix in the middle. So why am I doing this setup? Because now I could take exactly the same thing I had before, but instead of having E lambda E transpose, I have E lambda to the half E transpose. Well, what's lambda to the half? All I've done is I've taken that matrix and I've gone to every element and I've just taken the square root. Okay, I'm going to call this V a half, and you'll understand why in a second. So we know we can take any matrix and we can split it. And we can split into this E transpose, and this nice diagonal matrix. Zeros everywhere, but numbers along the diagonals. As long as all those numbers are greater than 0, we know it's positive definite. As long as they're basically non-negative, we know that it's a non-negative definite. I then take that diagonal matrix, and every element along the diagonal, I take the square root. Positive square root. Simple as that. This I can now use as the equivalent of a matrix square root. Because now my V minus half, which is E lambda to the minus half E transpose, you can see that basically if I take, I should just explain what I've done there. So that's the lambda to a half. If now where I've got all these lambdas, I take the reciprocal, then I can define that as E to the minus a half. So that is basically the inverse. But you can see that V a half times V to the half equals V. So it's like I've got this matrix, which I call V a half, and when I times it by itself, I get V back. So it acts like the matrix version of a square root. I find that V to the minus half, V to the minus half, and I multiply these together, I get V to the minus 1. And finally, if I do V to the minus half, V to the minus half, I get I. So this V to the minus half, which we designed by splitting into this product, which we do quite nicely, having this special lambda in the middle, taking the square roots. If I take the square roots and take 1 over that, I get this V to the minus a half. It acts like the matrix equivalent of a square root. So how am I going to use this? Well, what we're going to do is, let's say I've got my model y equals x beta plus epsilon. Standard model, but the only difference is we know that our variance of epsilon is sigma squared v. Well, I take this v, it's nice, and I calculate the v to the minus a half, which I can do. I can split it into the e, the diagonal, I can take the square root, I can take 1 over the square root, and I've got that. And then what I'm going to do is I'm going to pre-multiply everything in here by this matrix. So I'm going to get a y star, which I get by taking this matrix, v to the minus half, and multiplying it by my y. I get my x star by basically taking my x and pre-multiplying it by v to the minus half. And finally I get my epsilon star by v to the minus half epsilon. So all I've done is I've pre-multiplied every term by this v minus a half. Well, the nice thing is, now if we look in our new epsilon star, our new epsilon star has an expected value of 0, so that's good. Well, what's the variance of our epsilon star? Our variance of our new adjusted epsilon is the variance of v to the half epsilon, fine. That's v to the minus a half, okay, it's nice and it's symmetric. Variance of epsilon, v to the minus half transpose. Substituting this in, the variance of epsilon is v sigma squared, being the sigma squared up. I've got this. This whole thing we've designed to be I. So in this new transform space where I've changed my x, my y, and my epsilons, now in this transform space, the variance of my epsilons is sigma squared I. We're back in the standard format. So Gauss theorem Markov applies, so we now know the blue is just going to be beta hat equals x star transpose x star minus 1 x star transpose y star. So basically we're putting in all our stars, they've all been pre-multiplied, and the variance of beta hat is sigma x squared. So it's like we've taken on a linear model, we said it's got a problem, look at its variance. We've found the proper adjustment, this v to the minus half. We've multiplied everything in this new space, and now everything's back in our standard least squares approach. You can show that basically substituting in and producing gives your, so now I'm going back and resubstituting in the fact that x star equals v to the minus a half x and y star equals v to the minus half. Substitute back in, simplify, we get this form. So it looks very similar. You've got this x transpose x to the minus 1, but in the middle you've got this v to the minus 1. X transpose v to the minus 1y. So it looks very similar with our generalized least squares. And our sigma squared is x transpose x to the minus 1, but we've got this extra v to the minus a half in there that's adjusting. Sometimes it's really simple. Sometimes you find that you don't have a very complicated v. All you have is that you want it to be all zeros everywhere in your v, but your diagonals would be different. This would be the case where your residuals are still uncorrelated, but they might not have the same standard deviation, common problem. And in that, we actually just call it a weighted least squares, because all you do is you have all your variance terms and you just have this adjusted weight which you apply to each term, which is 1 over the variance. And you can actually do it in R, in the LM, you can just put it in and say, here's my variances. Just to show what this does, I'm going to actually look at the very simple case where we look at what we call a weighted mean. So suppose we've got some observations y1 up to yn. They have an expected value I equals mu, so we'll have the same mean. But the variance of y equals sigma squared. They have different variances. If I did the ordinary least square estimates of y hat, I would just get mu, but my variance would be this term here. You can calculate it yourself. I might leave you to calculate that in an exam. That'd be fun for you, won't it? But you can actually instead try to get a better one than that. So that would be your standard one. You could do a better one where you could do the weighted least squares estimates. So you can say, fine, I set up in my linear model, I have x equals just 1. My beta now just equals the mu I care about. My v equals diagonal. I shove it in. And your weighted least squares estimates will be mu hat equals, and you can see I'm taking each term, and instead of sort of adding them all up and divided by n, I'm going to adjust them by a weight. And the weight is this term. And what it's doing is it's basically anything that has a high variance, it's down weighting it. Because if you think about it, if it has a lot of variability, when you come to make your estimate, you sort of don't want to give it as much weight. You want to go towards the things that have more precision. And that's what it's doing. And in fact, it works really nicely. You find the expected value is mu, which is 1. The variance is mu hat, which is this. And it's easy to check the Gauss Markov that this new variance that this new estimate of the sample mean works so much better. And as I said, this is what I'm trying to say is this new one, this weighted sample mean, gives greater weight to the observations of lower variance compared to OLS. And you can see, you know, stats by an inference, you probably have already looked at that as an unbiased estimator. So there you go, you have the generalized least squares. It's the first adaptation. We go, what happens when we don't have the variance of the epsilons is sigma squared I, but instead sigma squared V? How can we adjust? We basically adjust all our observations into a new space that we can actually use the old method. Okay? Next time, we're going to start looking at box Cox. See you next time.